Swayam Prabha. Digital India. Educated India.
Hello everyone, so welcome back. So in today's lecture we will discuss different types of decoding strategies. Okay, so if you remember, we have this encoder decoder model, right? So encoder decoder model, let's say the application is machine translation, let's say English to Hindi, input is English, right, and output is Hindi. So at every state, right, of the LSTM, or let's say transformer, we'll discuss later, right, we will produce a distribution, and from the distribution the task is to choose the right, the word which you want to essentially place at this position. Okay, so there are different greedy strategies, different top case strategies that people came up with, and today we will discuss some of the popular strategies. Let's look at the decoding strategy. So as I mentioned, in a sequence to sequence model where you are given a prompt or whatever, an input, right, and the input is C, okay, and that's the input to your encoder, and to your decoder you have already generated things till t-1, right? Let's say the input is I am going to school, and the output you have already generated may, right, may. Okay, then what's going to be my next word? So given the input C and the tokens I have generated so far, W sub less than T means whatever I have generated till t-1. Okay, what is going to be my word at the tth time? Okay, C is the input, W sub less than T are the tokens generated till now, and we are interested in the current token. So decoding is the process of choosing the next token to generate based on the probability distribution of a vocabulary, right, of that language. So now, if we purely do this based on greedy, let's say I choose the best probable word as my next token, that will have certain disadvantage. What would be the disadvantage? The disadvantage would be this would mostly be deterministic, and this would be not only deterministic but also sometimes the quality may also be good, because let's say the application is question answering, so for every question you always want the same answer to be generated by the model. The quality would be good, but the problem would be diversity, right? You won't be able to produce words which are creative, which are diverse, right, because you will end up producing only single word every time. It will not produce anything, any new output tokens given a specific input, right? Now of course for machine translation diversity is not important, innovation is not important, but let's say your input is that write a poem about something, right? So you do not want the model to produce the same response every time. Okay, you want the model to produce diverse responses. So to make a balance between quality and diversity, we need some strategy. So we have discussed greedy decoding, where, as I mentioned, so given the input, when it generates the outputs, let's say the input is I like pizza with lots of, and this is the probability distribution of our tokens, and you see that the word cheese has the maximum probability. So in greedy decoding you essentially choose the word cheese, right? For exhaustive decoding, what you do? For exhaustive decoding, you, let's say at th time, you produce all possible words that can come here, meaning the vocabulary words, and for every vocabulary word you see what would be the next vocabulary word, right? Again, a branch of size mod v. So at every position you have mod v options, right? And how many words are there? How many words you want to output? You want to output n number of words, right? So you have mod v to the power n possible sequences, which is not possible. Beam search we discussed. In beam search what we do, we choose, you know, a specific value of the beam size, which is k, for example, and then at every time you look at k most probable sequence, and essentially you keep on pruning those which don't come within this k probable sequence, and you move on, right? So greedy, exhaustive, beam search, three of them are deterministic, right? There is no stochasticity you know, associated with them, because, you know, greedy you choose the best one, which will always be the same. Exhaustive you have all possible options, and beam search also you look at k beams, right? So deterministic versus stochastic strategies. If you use greedy or exhaustive or beam search, right, you would end up producing accurate results, but the response will not be diverse. So we'll discuss three strategies today: top k, top p, and temperature sampling. Okay, so in random sampling what we do, I mean the worst case, right? So let's say so we have this distribution p of wi given c is the input. What we do, we randomly sample a word from the distribution, okay, and that's going to be my next word. Again, next you so at t you sample from the distribution, this would be wt. At t plus 1 your input is c and till time t. You have a distribution and you choose one randomly, and you keep on going till you generate the end of sentence, or, you know, the n number of tokens that you want to generate are all exhausted. Okay, it is purely random, and this is not a good strategy at all. In case of top k sampling, what you do, you first, this is a variation of random sampling, right, but with a bit difference here and there. You choose the number of tokens value that you want to generate, right, and let's say the number is k. That means you will now play with this k tokens, right? What you do at tth time, right, you have the distribution, you choose top k highly probable tokens, right, and then you renormalize the probabilities of these k tokens, right, and then now in the probability you have only k tokens, right, not mod v number of tokens, and from there you choose things randomly, right? So you are essentially doing random sampling within the top k tokens, not mod v tokens. Okay, let's look at example. Let's say k is 3, right? So this is my total, the entire probability distribution, right? You choose top 3, cheese, toppings and pepperoni, right, and this is their probabilities, and now this is your candidate probability. These are your candidate probabilities. Now here, so now you renormalize this, right? So if you renormalize, then for cheese this is going to be 0.35 plus 0.35 plus 0.2 plus 1.2, right? For toppings, this would be, I mean, you can do in this way or you can do in a softmax way, right? Which would be exponential of e to the power of this, right? For topping, this would be 0.2 by 0.35 plus 0.2 plus 0.12 and so on and so forth. So once you do this renormalization, right, this is your resultant probability distribution. Okay, now you choose things randomly from this distribution, not from this, right? So you are restricted to k number of tokens now, but you are doing random sampling. So this is top k. So the problem with top k sampling is that let's say you have a skewed distribution like this, okay, where top k words will encompass the probabilities of the top k words will encompass the entire probability mass, right? Let's say in this case, if you take this and this and this will be more or less the entire probability, right? Whereas and if you have the distribution like this, then top k makes sense. Whereas if you have a kind of uniform distribution like this, if you fix the value of k as 3 or 4, right, you will, let's say k is 3, so you would end up choosing only 3 words for your candidates, right? And the remaining words are also equally likely because they also have similar probabilities. So in this case, top k doesn't make any sense. Okay, so instead of fixing k, which is the number of tokens that you want to play with, if we can choose the certain probability, and you say that look, my probability threshold is, or cumulative probability threshold is 0.6, and I will start from highly probable word, then the next one, and I will keep on adding, you know, the top probabilities and keep on choosing those corresponding words until unless the threshold is met. Okay, so now we have a threshold on the probability, not the number of tokens. Okay, and this is exactly top k sampling or nuclear sampling. Okay, so you choose top k vocabulary, right, which is the smallest set of tokens such that this satisfies. Smallest set, this is important. Let's take an example. Let's say this is my actual distribution, right, and let's say let's take some of the top probabilities, right, and these are the top probabilities. If we choose cheese, the cumulative probability would be 0.35. If you choose toppings after that, this would be 0.35 plus 0.0, 0.2, 0.55 and so on and so forth, right? So let's say the P is 0.5. Okay, so it means the threshold is 0.5. It means that if I choose this and this, the sum of the probability would cross 0.5. I will essentially choose 0.35 and 0.2, right? That would basically exhaust my total probability budget, and then I do the same. I'll take these two words, probabilities, renormalize them, and then do random sampling, right? So in this case, cheese and toppings would be enough. If we do random sampling, if we do renormalization, this is the renormalized probability, and then we do random sampling. Okay, so the advantage here is that let's say you have a uniform distribution. Let's say the distribution, the probabilities look like this: 0.2, 0.2, 0.1, 0.1, right? Or let's say 0.05, 0.05 and so on and so forth, right? So in that case, if the threshold is 0.5, you will end up choosing this, and maybe this, because it is greater than 0.5. If it is greater than 0.5, then you choose this and this. If it is skewed like this, then you end up choosing only 2, right? So this is the beauty of top K sampling. The remaining one is temperature sampling, and this is very simple. So in temperature sampling, we do not truncate the entire distribution. It's not like from the distribution I choose top 3 or top 4, whatever, top 3. Here I use a new hyperparameter, which is the temperature parameter called tau, right? And the hyperparameter, so this is my softmax probability based on which I create the distribution, and this is my softmax in temperature, right? You see the temperature here, the actual logit by the tau parameter. Okay, now if tau is 1, then this is same as the random softmax probability. If tau is low, 0.1 for example, you would end up, think about it, tau is low, that means this would be high, right? Versus if tau is high, then this would be low, the exponent would be low. So if tau is low, you are kind of promoting more skewedness, right? So if tau is low, you would see a skewed distribution, and then you can choose the top 1 or top 2, whatever. If tau is high, it will be more of an uniform distribution. So you can play with this temperature parameter tau, and if you want to be deterministic, then you always choose the lower value of tau. If you want to be more stochastic, probabilistic, right, more variation, more diversity, right, you should choose high value of tau, right, depending upon your application. This is a very important hyperparameter. Okay, so this is written here. If you want to be creative, your tau should be higher. If you want to be deterministic, tau should be lower, and this is tau equals to 1 is the regular softmax probability. That's it. So this is about decoding. Now this part is complete. In the next lecture, we'll move to the next part. Thank you.